Hello everyone. In this session, we'll try to understand how to model the trend in the data, what kind of trend-based models we can create given a data, and using those models, how can I forecast the futuristic values based on the trend. So that is what we are going to look at here. So what do we mean by trend? Is something we want to initially look at. Then differentiate between a linear trend versus a non-linear trend. Then how do I estimate the trend model? So here I want to take up a data set, and on that data set I want to really apply different kinds of trend models and see for this particular data set which particular model is a much appropriate fitment. Right, so I want to estimate different kinds of trend models. We will look at three of them here. We will see a linear trend, we would see a quadratic trend, and we would also look at an exponential trend. And like that you can even give any number of trends as such. But different kinds of trend models, how do I fit them to a data is something that I want to look at here. Based on those trends, based on those models that I have come up, I want to do the futuristic predictions. Right? So if a particular data follows a linear trend, what would be the value for the future? If it follows a quadratic trend, what is the estimate for the future, or what is the forecast for the future? Similarly, an exponential trend. Now I have different models with me. So what is the criteria to really select which model is more appropriate for the data? What are the different kinds of selection criteria that are there? Once I create a model, how do I really decide whether model 1 is good for the data or model 2 or model 3? Which model is good for the data? How do I really assess it? That I have to do using the various model selection criteria. So I really want to use different kinds of model selection criteria. I need to understand different kinds of model selection criteria so that I can really choose which model is more appropriate to my data. And what is the consistency? How do I really measure a particular criteria? What is the layer of consistency that is associated with it? So these are the various things. So a little part of it is conceptual in nature, whereas some part of it is more practical, where I may have to execute it with my data set. So we all know the word trend, right? Here in the trend, we always talk about three types, either an uptrend or a downtrend, or increasing trend and a decreasing trend. And if it is flat, we typically call it as no trend. So whenever we are using the word trend, it's a slow, long run. So we are not talking about a few days. We don't use the word trend. It's more of long run evolution in the variables that we want to model and forecast. Let's say I want to model the price. I'm looking at month over month or year over year. How are the prices typically evolving? Right? It's a gradual, slow increase or a decrease kind of stuff over a long run. So generally, trend is produced by evolving preferences. Right? The customers' buying behaviors change. So based on that, overall, in a long run, I see that the sales of a particular product will typically go up or go down. Technologies keep changing. So the telephones versus the cell phones. So once the mobile phones came up and then probably the smartphones came up, that's a change in technology. And the sales of the smartphones are typically going in an upward direction. When I look at it over a very long run pattern, how these sales are typically emerging. So the drivers are the change in the preferences of the tastes of the customers. Technology could be a driving factor. The institutions which are promoting them, that could be a different factor altogether, and demographics, aged people versus the new generation. So each with the change of generation, we may see that the tastes and preferences, a lot of things are changing, which means the trend with respect to a few products will be increasing. The trend with respect to a few products could be decreasing. If I am able to predict the trend to a large extent in a predictable way, it will go up or it will go down. That portion of the trend is what we are calling as the deterministic trend. But that part of the trend which is not predictable, which is more and more random in nature, which can't be predicted through any mechanism, we are calling it as a random trend or probably a stochastic trend. So here our focus is more towards the deterministic trend itself rather than the stochastic component of it. Now, while defining the trend, we generally use two different definitions. One, a linear trend, the other one being a non-linear trend. Right? In a linear trend, we see that the trend either increases or decreases in a straight line. So if I'm talking about the price, typically, okay, 100, 120, the next period 140, approximately around that, 160. So there is a kind of a linear increase. So the change is more or less constant. The change between the two time periods is more or less constant. So here this is a linear function of time. Typically I can write the equation as a linear equation, y equal to a plus bx. So here the x for me is the time variable. So beta naught and beta 1 are the beta naught is the intercept, which is like if time is 0, the value is beta naught, which is the value in the first period. Right, at time 0. We are talking about the trend at time 0. Whereas when we are talking about time is 1, then we are talking about the trend value as beta naught plus beta 1. So beta 1 is actually called as a slope. So if this beta 1 value is positive, it means it's an increasing trend. If the beta 1 value is negative, I can interpret it as a decreasing trend. And the time, so when we represent the time, so the first period will represent it as 1, the second period as 2, and the 100th period will represent as 100. So this is the typical equation we write for a linear trend. When we do this on a data set, this becomes more and more clear to you. But just to understand a few terms, time equals 1 in the first period, 2 in the second period, 100 in the 100th period. If I am talking about monthly data, first month I'll represent it by 1, the second month I'll represent it by 2, 100th month I'll represent it by 100. So this equation has an intercept, which is the value of the trend when time equal to 0, slope, which will be either positive or negative. If it is positive, probably I'll get a graph which is like an increasing trend. If it is negative, I'll get a graph which is more like a decreasing trend with time. And I could also have a non-linear or a curved kind of trend as well. So the variable value, it increases or decreases, but not as a straight line. It's not a constant increase or a constant decrease. It could increase at an increasing rate, or it could increase at a decreasing rate. It could decrease at an increasing rate or decrease at a decreasing rate. All kinds of possibilities are there. So which means you are getting a curve, not a straight line with respect to the non-linear trend. That's the reason we call it as a curved trend. So typically we can talk about a quadratic trend or an exponential trend when we use the word non-linear trend. Quadratic trend is typically a plus bx plus cx squared. So it's a quadratic expression, a plus bx plus cx squared. So you could take it to any kind of polynomial. Probably I can take the cube to the power of 4s, etc. But that makes the model very, very complex. So generally it is suggested to use the lower order polynomials itself so that the smoothness can very well be maintained. But otherwise you can extend it to any kind of level of polynomials because all of them will show some kind of a curves in the pattern. So different nonlinear quadratic trend shapes are possible. Now if you are talking about a plus bx plus cx squared, right, let me just try these things. So let me take the values of x, right, I'll take the values of x as, let's say, 0.1, 0.2, and let me take it up to 10 or 5, right, I'm taking the values up to 5. So I want to take the values of a, b, c. So let me take a and a, b, c, both of them are positive. So let me take 1, 2, 3, right? And now let me take the value of y, which is a plus bx plus cx squared. So I'll take it as a plus b times x plus c times x squared. If I take this, okay, these are the values of y. Now I want to plot this graph, right, wherein you could see here in this example, both here the importance is with a, b and c, these two coefficients, beta 1, beta 2. Both the time coefficients are positive. Let's say both of them are positive. So that is what is the case out here. Then if I am trying to plot this graph, look at the outcome of this graph. If I am trying to plot this graph, it is like an increasing kind of a trend. You see the graph is not linearly going up, it is going up non-linearly. Trend is monotonically but non-linearly increasing when both the coefficients of time bx and cx squared, b and c, both of them are positive. But look at the scenario when both of them typically go negative. Right, look at the scenario when both of them go negative. Let's say I put -2 and -3. I could see that it's a completely falling kind of a trend. Irrespective of whatever the A is, if B and C are both of them are negative, which are the two time coefficients, one is the linear, the first degree coefficient and the other one is the second degree coefficient, both of them are negative, I see a kind of a decreasing trend. But if one of them is positive and the other one is negative, let's say I said this, the B is positive and C is negative, some kind of a U shape is bound to occur, though we are not able to see it clearly out here. One is positive, the other one is negative, it's a U shape that is going to occur. Whereas the same logic here, in some cases it's a U and some cases it's going to be an inverted U. But that's not a kind of a increasing or a decreasing kind of a trend. You'll see the complete U or an inverted U depending on what are the values of X I am typically considering. So those are the different kinds of shapes that are possible with nonlinear quadratic trend depending on the coefficients that are associated with time as well as the time squared. And it's very appropriate for stock markets, volumes data, price data. We can very well look at all these kinds of models. Similarly, as I was talking of, exponential trend is also very much possible. So overall the trend appears non-linear, but the moment I take the logarithm of the values, there is a possibility that the trend appears linear. If I am taking the values as it is, the trend is appearing non-linear. But if I am taking the logarithm of the values, the trend looks linear. So that is what here I am trying to put. Log t, so which means the trend is called as an exponential trend, which you find very common in finance, where we see the economic variables display roughly constant growth rates. So the way we represent it is beta naught, instead of saying beta naught plus beta 1 times time, that is what is the linear trend, we said beta naught into e to the power of beta 1 times time. That is what we are calling as exponential trend. So which actually works out, if you take the logarithm on both sides, it works out as log trend is equal to log beta naught plus beta 1 times time. So after you have taken the logarithm, it looks like there is a linearity that is present. In that case, the original trend is what we are calling as an exponential trend. So these are the different kinds of trends we need to be aware of, and we need to see with respect to our data which trend is more and more appropriate. Is it a linear trend, or if it is a non-linear trend, is it quadratic trend that is more appropriate, or an exponential trend? Right? Now, estimating the trend model. So we have already talked about three types of trends. So I want to estimate the various trend models to a data using the least squares regression method. What I am doing here is, if you see here, y equal to a plus bx. Now there will be some kind of an error term. Now the error term is what we can write it as y minus a minus bx. Similarly, in a quadratic trend, it would be y equal to a plus bx plus cx squared plus some error term. Here also we can write the error term as y minus a minus bx minus cx squared. Now, while doing the estimate, for every observation, I want this to be applicable, right? So, this error, the total error is what I want to minimize. But I don't want to take the absolute error or the actual error. I take the squared error, which means this part. Across all the observations, I want to take this and I want to minimize it. Similarly, here also that's the same process. So whatever is the model that I am fitting, I want to take the actual minus the expected in each of the cases, and I want to minimize that error. Let's see in the data. First, let's fit a linear model. Right, let me not look at this aspect. So let's go. With this, I have the data of Sensex, which is the Indian Stock Exchange, the values of the Sensex right from January 2001 to December 2016. Okay, let me not consider December 2016 as we are just a week into this particular month, up to November 16. So I have the data over almost 16 years monthly data. Now I want to do a trend fitting out here. First of all, I require the time variable time. So as we said, the first month we'll represent it as 1, the second month we'll represent it as 2, and it continues, which means the last month is represented as 191. And we also have a time squared to talk about the quadratic trend. So I will take the square of this to represent the quadratic trend. So that's how I have the quadratic values or the squared values as well till the last. Now I want to fix a linear trend, right? So here let me say I want to go with a linear trend. So for the linear trend, I require two variables a and b, a plus bx. So a and b are the two values that I require. Initially I am just going with some dummy values 100 and 1. So based on this, I am going with predicted linear. I am creating a column called predicted linear, which is like a plus bx. So I'm taking it as A plus B times X, which is the time. So this is what is the predicted value going with this kind of a model. So based on this, I can talk about the error term, which is y minus of A plus Bx, right? Error linear, which works out as y minus of A plus Bx. So this is A plus Bx, and I'm taking y is the actual value minus the predicted value. This is the error part. So this is the way the error is coming out. Then we are talking about, I want to minimize this error, but not in the original form, but the squared error. So that's where I call error linear squared, which actually comes out as this number squared. I want to minimize this total error, right? So let me give few more columns. So here, total squared error, I want to look at it, which is the summation of all these things. This is the total squared error. I want to change the values of A and B, right? Those are the estimated values. I want to estimate the values of A and B in such a way that this error is the minimum most possible. So I can use various mechanisms to do that. I can use the maxima and minima theoretical aspect, but when I'm working with a tool like Excel, I can very well use the solver. I'll use the solver where this particular value need to be minimized by changing these two values. That's it. And I am not making any kind of positives or negatives. I am not constraining any of the variables. Based on that, when I got this kind of an equation where A is 1121, B is 138. And in that process, I am getting this is the error and this is the error square. And this is the total amount of error. Right? This is the total amount of error, squared error. Right? This is the total amount of squared error. And that is the minimum most possible when I am going with a linear model. This is what is the least possible error I was able to get when I am going with the linear trend. So the equation typically for me, if I am going with a linear trend, the best possible equation for me is 1121.918 plus 138.42 times the time. This is the kind of model that we have got. So the intercept is 1121 and the slope is 138.42, which is positive, indicating that on an average per month the index value is increasing at the rate of 138.42 points. On an average every month I am looking at the index growing at 138.42 points. That is how I am looking at the linear trend model. Now I want to look at the quadratic trend model, right? If I want quadratic trend model, I require A, B and C. Here also let me start with 100, 1 and 1. Now based on that I have predicted quadratic values which will come out as A plus B times X plus C times X squared, which is the time squared. So this is what is coming out as the predicted values. And based on that I can get error quadratic, which comes out as the predicted, the actual value for that period minus the predicted value, working out to this much. and based on that I can very well take error quadratic squared, which is working out to the square of this particular number. So I can now look at the total squared error in this case, quadratic case, which is working out to this much. So here the quadratic error is to the extent of 4,785 million, 4.7 billion. Here the total squared error is 1.025 billion, whereas here it came out to 4.785 billion. Now, yes, I have to get the optimized values. These are some dummy values that I have started off with. Now, I'll optimize that values by setting this particular value to be minimum, wherein I have the flexibility to change these three values and try to see the minimum most error. Here it looked like the total squared error is 1.023 million. Here it is 1.025 million and here it worked out to 1.023 million. And in this we got the expression like this, 1372. If I am fitting a quadratic model, it is like 1372.67 plus 130.625 times time plus 0.04 times time squared. So the coefficient for time squared is a very small coefficient, but that is what is the best possible equation that we have got when we are going with the quadratic trend. Then what about the exponential trend? For the exponential trend, we need to take the logarithm of the dependent variable. We are not taking the dependent variable as it is, right? So this is where I'll take log sense x, where we are considering the logarithm of the dependent variable. I'm taking the logarithm of this one. So these are the log values. Now the time is still the same. So let's go with the exponential trend. Wherein again, because I am taking only two variables out here, a and b, or beta naught and beta 1, whatever it is, and I could again take some 10 as this and 1 as this. I'll take a predicted value. So I am saying predict underscore exponential, where I am putting it as a plus b times the time. The time is this one. So this is how the predicted values have come in the exponential model. Based on that, I am talking about error underscore exponential, which is the difference between the actual and the predicted. And taking the squared, we get error underscore exponential squared, which again is this number. We are doing a squaring, which is giving me the error exponential square. So from here I can get my total squared error for this purpose. Total squared error is working out to be this much. Now this is to the extent of 2.35 million. But yes, I want to play around with the values of a and b in such a way that the total error is going to be the minimum most. So I am minimizing this total error by changing these two parameters, resulting in 8.193. Okay, this is how it goes now. Log sense x is equal to 8.1937 plus 0.012 times time. So this is what, so basically if I want the sense x, it would nothing be, it would be e to the power of this much, 8.1937 plus 0.012 times time. So this is what will become the function in case I want to look at the model for Sensex. So these are the typical numbers that I am considering for the linear trend, for the quadratic trend, and for the exponential trend. So these are my three models going out with the estimating the trend model. So the best possible linear trend model here is 1121 plus 138.42 times time. For the same data, the best possible quadratic trend model is this one. And for that same data, the best possible exponential trend model is working out to be this one. So these are the things that we are considering right away. The three trends, if I have to estimate, these are the numbers. But now I have a requirement of forecasting the trend. So I have to take it as y t plus h for some h periods in the future. That is what we are calling as t plus h. T is the current period and h is the number of periods in future. So when I say t plus 1, it's the next period, t plus 2 is the period after that, and so on. So the formula that is coming up, beta naught, which we have already got. So the coefficients and their variables, time t plus h, and epsilon t plus h is very important because time t plus h is already known, because 191, if it is November 2016, if the number is 191, December 2016 will become 192 from my data, Jan 2017 will become 193, and so on. So we know the time t plus h, but epsilon t plus h, the error at that particular point, we don't know. So that is where we say we will replace it with an optimal forecast of the error constructed up to the time t, and generally we take it as 0. For this estimation purpose, the epsilon t, we are taking it as 0. So we will be using only the coefficients and their associated values. And the unknown parameters are estimated through the least square estimates. That is what we got. These are the coefficients for a linear model. Beta naught, beta 1. Beta naught, beta 1, beta 2. Similarly, exponential, beta naught and beta 1. So this is what, if I really want the predictions now for December. Right, if I am looking at the prediction for December 2016 out here, let me take here itself. Right, prediction December 2016, which is what is nothing but A plus B times the next period. The November 2016 is 191. So it is 192. So I say this times 192. So as per this, the predicted value for December 2016 is going to be 27,698. But now if I am going with the quadratic trend model, again predicted value for December 2016 will be A plus B times X, which is 192, plus C times X squared, which is 192 squared. So going with this model, the December's forecast is going to be 27,949. That would be the value of Sensex for December 2016 going with the quadratic trend. Then similarly predicted December 2016 forecast going with the exponential trend A plus B times 192. So this is the predicted value for December 2016, but this is log Sensex. So I have to take the EXP of this to get my Sensex value. Right? So I'll take EXP of this to get my Sensex estimate for 2016 December. Oh, this model says the expected value of the Sensex in December 2016 is 37,429. It's looking like pretty much on the higher side. Now, so we have got the estimated values for the next period. Now I want to go with an interval forecast. So if I want to go with an interval forecast, I really need to know what is the typical error part of it. So this makes an assumption that whatever is the error part, it is normally distributed. So the error part is normally distributed. So we have the error terms in all the cases. This is an error term, this is an error term, and this is an error term. So here it assumes that the error part is normally distributed. And based on this, we get the 95% interval forecast as plus or minus 1.96 times sigma. So if I am able to compute the sigma in each of the errors, I can very well take the 95% interval as plus or minus 1.96 times sigma. So what I can very well say here I can very well look at what is the sigma value. So error sigma, which is the error's standard deviation. So I am using the standard deviation of the linear predicted model's error. So it says the error is to the extent of 2323. Here also I can very well find out what is the error sigma. The error we are assuming it as normally distributed. The error terms are being assumed as normally distributed. So I am taking this error term here, which gives 2320, and I can also take error here, which would be on the log terms. Right, the error is associated with the log terms out here. So I can look at the standard deviation of the logarithmic Sensex. So which gives me that the error is to the extent of 0.26. So based on that, I can very well find out that the 95% interval forecast is plus or minus 1.96 sigma. So whatever is the predicted value I have got, I can very well go with plus or minus 1.96 sigma. So if I am talking of lower interval as a part of my forecast, going with a lower interval, it is nothing but the predicted value minus 1.96 times the sigma. This is the lower interval of my prediction, and upper interval comes out as the predicted value, which is 27,000 plus 1.96 times the sigma. So this model says the range is the 95% confidence interval range for the prediction of December is 23,144 to 32,252. That's the range that is being specified by this model. But now I can see my other models as well. So this model, if I go with lower interval, it comes out as the predicted value minus 1.96 times the sigma, which is saying 23,400, and upper interval is saying the predicted value plus 1.96 times the sigma. So this is talking about 32,498. So it's talking about a range of 23,400 to 32,498 as the range for the value of Sensex for the next month. Going with this one, the predicted value, actually let me take it without the EXP, because I require the predicted value and the actual value. So here I'll take the EXP in a separate cell, right? So lower interval for me, first of all I'll compute the logarithm based lower interval, which is 10.53 minus 1.96 times sigma, and the upper interval again for the logarithmic terms, I am getting it as the predicted value plus 1.96 times sigma. Now if I am translating the same into the original values where I am taking the exponent, it says it can range anywhere between 22,000, that's on the lower side, to 62,000 on the very much on the higher side. So probably here I am looking that the error, the range is much higher, anywhere between 22,000 to 62,000 for the value of Sensex next month, going with the trend. Whereas with the quadratic trend and linear trend, these are the 95% confidence intervals. So only if I am taking the interval, I will talk about plus or minus 1.96. And if I am talking of the density, I will take the predicted value plus or minus 1.96 times the sigma. So both of them are considered when I am looking at the density forecast. So these are the trend forecasts that I have got for my data for these three kinds of trend models. Now that I have these many models in front of me, I need to know what are the ways in which I can select which model is the best. Right? I need to know that the model selection, I need to understand that the model selection is very important in this forecasting exercise. So one side is I am taking the mean squared error. We have the total squared error here. If I had divided it by the total number of observations, which in our case is 191, so this number, right, this number divided by 191 is giving me the mean squared error. Here also mean squared error is coming out as the total squared error divided by 191. Here also when I am looking at the mean squared error, I am taking the total squared error divided by 191. So that's what is coming out as the mean squared error. So the most model selection criteria attempt to find the model with the smallest out of the sample one step ahead mean squared error prediction error. So that is what we have got here. We looked at the error squares of all the terms and we have divided it by t, which is the total number of periods. That is what we are calling as the mean squared error. So the model with the smallest mean squared error is also the model with the smallest sum of squared residuals, because in all the cases I am dividing it by t, which is the total number of observations, which will not have any kind of an impact in the overall interpretation of the model, right? Because if the sum of the total errors is lesser, even the division by t would be lesser, and if the sum of the errors is higher, so if the total error is higher, the mean squared error is also higher. Total error is lower, the mean squared error is also lower. That is how we can bring out the relationship. Then we are talking about the other term, which is the R squared. So we are talking of it simply as 1 minus of, if you look at this here, 1 minus of the total error. So in the numerator we are seeing the total error, total squared error that we have already computed. But in the denominator we are talking of each observation minus the mean square. We take each observation minus the mean square. So what I would like to take there is, for the linear, I am taking the each observation minus the mean squared. which is coming out as, this is the observation minus the mean. I can take the average of these values. The observation minus the mean, I am taking the squared of that. Right? This is in case of linear. Remember, whatever is the case, for linear and quadratic, both of these will be the same because observation minus the mean of it squared. So for linear and quadratic, this number is going to be the same. But for exponential, it would be different because we have worked it on log. So in case of exponential, I can very well take it as, this is the observation minus the mean of these observations. I'm taking the square of it because I want to compute the r squared. I want this value in the denominator. So I can take the total. So when I'm taking this total, it is what is typically called as the total sum of squares. This value is actually called as the total sum of squares, TSS. So I will take the total sum of squares as one more thing, the TSS, which is the total sum of squares, where I am taking the summation of this out here. Here also, when I am going with the total sum of squares, again it would be the same thing. Each observation I have subtracted the mean from it. So the total sum of squares is going to be the same here as well. Whereas here the total sum of squares will be different because we have done it on the exponential. So this is what is coming out as the total sum of squares. And based on this, I should be able to compute the r squared of the model, which is going with that formula that I have shown. So we will go ahead with, based on this, we are computing the total sum of squares. So here let me take the exp. Okay, so now I can find out the total sum of squares. We have already found out the total sum of squares, and based on that now I can find out the r squared, which is going as 1 minus of the total squared error divided by the total sum of squares. So that gives r squared, right, which is 1 minus of total squared error divided by the total sum of squares here, giving me 91.55% r squared there. And here when I look at the r squared, it is 1 minus of total squared error divided by total sum of squares, making it 91.57%. Whereas here when I am looking at r squared, it is again 1 minus of total squared error divided by the total sum of squares, taking the value to 86.88. So one way of looking at it is, the denominator is the total sum of squares we have computed, which is nothing but each observation, subtract the mean from it, square it and add it. That is what we are calling as the total sum of squares. Obvious thing is, if I am looking at it on a very base note, the one that is having the highest r squared would be a much better model. But need not be a better model if I am doing a prediction part. Out of the sample forecasting is, if I did not use that value for building the model, but I am still using it for forecasting purpose, the result that may not be good at all. So because of this relation, If I am selecting a model that is minimizing the mean squared error, internally it can be understood that this is the same model that will maximize the R squared value also. So in this case you could see that the R squared is 91.57 here and it is 91.55 here. So I may be tempted that the R squared is highest in the quadratic trend model. So I should go with using the quadratic trend model for the prediction purposes, for the future forecasting purposes. But couple of points regarding this. If more variables are included in a forecasting model, what we see is the sum of the squared residuals will keep going down only. Means the R squared will only keep going up irrespective of whether the values are relevant or irrelevant or whatever it is, whether the variables are relevant or irrelevant. Even if it does not go up, the R squared value will be stable, but it will never come down. The more the number of variables we are adding, the higher will be the R squared itself. But it could be marginally higher like this, 91.55 here. We added one more variable times squared. The R squared became 91.57. It can't become 91.2 or 90 or something. The minimum is because it will assign a coefficient of 0 for C and still it becomes a linear model. And if it is a linear model, still you could see that the 91.5 should be there. So there is no way that the R squared of the model will come below 91.55 at all. It will only keep growing. If the variable is significant, it will grow much differently. If the new variable is insignificant, there would be a very marginal growth. So we see that the more the number of variables we are including in a forecasting model, the sum of squared residuals will be lower, which so the error part could be much lower. So here you could see here the error part in the first case is 1.025 million. Here it became 1.023 million. So the error part will keep coming down. But that could result in a very big overfitting on the in sample. In sample things could be much better. But if I am doing it for the using it for the forecasting purpose, I'll have some bad results coming out altogether. So this is where I have to be slightly more careful when I am using a data for a prediction purpose. So depending on the number of variables that are being used, there should be some level of penalization that has to be done to obtain with a criteria for evaluating the various models. So out of that, one mechanism that is used for assessing the performance of the models is S squared. S squared is the usual unbiased estimate of the regression disturbance function variance. So we are dividing the total error squared by t minus k. T is the total number of observations. K is the number of parameters that coefficients that we have, number of parameters that we have used in the model. So in linear model it's only one parameter, time. In quadratic it is 2, time and time squared. And again in case of exponential it is only one variable, that is the time. So in that case I could also find out S squared, and using the S squared I can very well estimate which model is better and which model is worse. So if I look at S squared here, it's nothing but the total squared error that I have got. I have to divide it by t minus k. K is 1 here, t is 191. So here the S squared is working out to almost 5 million. 5.39 million is the S squared here. Whereas here the S squared is coming out to the total error t minus k. Here there are two, value of k is 2 for the quadratic trend. So that's the reason I can do 191 minus 2, 189, resulting in S squared value of 5.41 million, whereas it is only 5.39 million. So this is where I say Still, going with the S squared, this model may be still a better model, because the S squared, no, this is error. I want the S squared to be as minimal as possible. So between these two models, I can still select the one that is a linear model itself compared to a quadratic model, because the S squared is only 5.39 million there, whereas it is 5.41 million here. And here comes the S squared for this particular data, which is coming out as this divided by 190. So this is what is the S squared that is coming out here. Similarly, we also have another mechanism called adjusted R square, which actually works out like this: 1 minus of the total error divided by t minus k, which is S squared, and here denominator we have the total sum of squares divided by t minus 1, which is the total number of observations. That is called 1 less than the total number of observations, and that is what we are calling as adjusted R square. This is also one more measure that we can use for comparison purposes. So in this case, I can talk about adjusted R squared, which comes out as 1 minus of S squared divided by, I am talking about total sum of squares divided by t minus 1. Sorry, total sum of squares divided by t minus 1. So this is the total sum of squares divided by t minus 1 is 190. Based on this, I am getting the adjusted R squared here slightly 91.55% out here when I am going with the adjusted R squared. But if I look at the adjusted R squared here, we are getting 1 minus of S squared divided by the total sum of squares divided by 190. This is the total sum of squares divided by 190 is giving me the adjusted R squared is only 91.53 here, whereas it is 91.55 here. So you could see that the adjusted R squared has actually gone down, which means even if I am going with adjusted R squared as a phenomenon for comparing the models, I see that the adjusted R squared for the linear model is much higher compared to that of the quadratic trend model. Even here the R squared itself is lesser, so adjusted R squared I can expect it to be nowhere coming closer to 91 at all. So wherein I have my 1 minus of S squared divided by the total sum of squares divided by 190, resulting in the adjusted R squared also to be the same. If the number of variables is 1, using this formula, the adjusted R squared will be exactly same as your R squared itself. But the more the number of variables are increasing, this is where you could see that the adjusted R squared will keep coming lesser and lesser compared to your R squared value, which is a kind of a penalty for more number of parameters being used. Unless the R squared is significantly higher after covering that penalty, there is no need of including that additional variable as a part of our model building for forecasting purposes. So here it is very clear. Even when you looked at S squared, it looked like the linear trend is better than the quadratic trend. Directly I am eliminating the exponential trend because the R squared is quite pathetic compared to the linear and the quadratic trend. So even when I have used S squared, it looks like the linear trend is better than the quadratic trend for this data, because linear, the S squared, which is a measure of error, is 5.39, whereas here it is 5.41 million. Adjusted R squared needs to be higher. I see that it is higher in case of linear trend compared to a quadratic trend. So using these two models, we are able to see that for the linear trend, the numbers are better. The accuracy of the linear trend model is better compared to that of the quadratic trend model. And we have a few more other criteria also to check. But this is what is, as of now, this is what is the situation between the linear and the quadratic trends using the S squared and the adjusted R squared as the measures, right? Now, looking at couple of other methods which can help me to accomplish the same. All those models, they have to penalize the in-sample residual variance, which is the mean squared error, to reflect the degrees of freedom that they are using. So based on the number of parameters that are being used to estimate the model, I have to deduct, or I have to have some kind of a mechanism to penalize based on the number of parameters being used. For that condition, we have one more thing called Akaike Information Criteria, AIC, which typically is again a kind of an error. If you look at it, this is the squared error, and divided by t, which is the average squared error, which is the mean squared error. So this part is the mean squared error. The mean squared error, I am raising it to the power, to multiplying it with e to the power of 2k by t. That is what is the AIC. I am multiplying it with e to the power of 2k by t, where k is the number of parameters, right? So in case of linear model and exponential model, they are 1, and in case of quadratic model, they are 2, right? That's how I am getting my AIC. So in this case, if I am using AIC, it is, I am taking the mean squared error, this is the mean squared error, multiplying it with e to the power of 2k by t. So I am multiplying this with e to the power of 2 by t is 191. So this is what is my AIC. So in this case, the AIC is 5.42 million. Whereas here, if I am looking at AIC, again it's a mean squared error multiplied by e to the power of 2k is 4 by 191. So here the AIC is 5.47 million, whereas here it is 5.42 million. So again I could see that the AIC is lesser in case of linear trend compared to a logarithm, compared to a quadratic trend. So that's the reason, even going with the AIC model, I see that the first one is much more, the linear trend is much more appropriate compared to a quadratic trend. Right? So even going with AIC, Akaike Information Criteria also, the conclusion is coming out to be the same. Now let's look at one more, which is Schwartz Information Criteria, SIC. Sometimes people call this as Bayesian Information Criteria also. Which is otherwise called BIC. The way you are taking that is, again, this is the mean squared error. If you look at it, you are multiplying it with t to the power of k by t. That is the way the Schwartz Information Criteria is computed. The mean squared error is multiplied by t to the power of k by t. So SIC is computed as here the mean squared error multiplied by t to the power of k by t. K is 1 here, 1 by 191. So the SIC is working out to 5.519 million out here. Whereas here when I am looking at SIC, again 191 to the power of k. Here the k is 2. 2 by 191. Taking it to, you have to multiply this by the mean squared error, making it 5.66. So you could see that the SIC is much higher here, SIC is much lesser in case of linear trend. Even that is a kind of a measure which says based on SIC, AIC, adjusted R squared, S squared, all these things for this example they are suggesting that I should rely on the linear trend as a better predictor for this model compared to a quadratic trend. If you look at all these, they are penalty factors, some kind of a function of k by t, where the number of parameters and total number of observations are typically looked at. So k by t is nothing but number of parameters per sample observation. So there is some kind of a kind of penalization that is getting applied, and the lower the error, the better it is. Different criteria are penalizing the degrees of freedom differently, but as long as we are talking of AICs, BICs, the measure of errors, the lower they are, the better is the model. Now that we know that there are different kinds of criteria for selecting a particular model, I am more interested in looking at how do I assess the consistency of the model. So I'm here looking at evaluating the model selection criteria. So how do I go with, let's say I have considered 4 models, right? The linear trend, the quadratic trend, the exponential trend. So these are some of the models that I have considered. Now I look at the true model, which is the actual one. So this is what I am calling as a data generation process, DGP. So if this is there as a part of any of these models, then what we are saying is the probability of selecting this true one based on these, the probability of selecting the true one has to go to 1 as the sample size increases, which means somewhere it has to approach here. Right? So this is one important thing we have to consider. As the sample size increases, probably the chances of estimating the true model should increase, it should come to 1. But if the true model is not there as a part of these, let's say the true model is following some other kind of a process, it's not one of these 3 processes or models at all, then it is impossible to select the true data generation process. And the probability of selecting the best approximation out of these, I want to look at the best approximation, that out of these which one is the best, the probability should be 1 as the sample size is getting larger. Because there is no way I can ensure that my model is 100% correct. All of them may be false. Because what we are trying to do while creating a model is we are trying to simplify the reality. The reality is very complex. The way the data can follow in real world is not directly a linear model or an exponential model, etc. It could be much more complex. We are trying to make that kind of a simplicity out of that complex reality. Now this is where we should understand the different models or different error selection criteria that we have. The more of a consistent model means if I am increasing the sample size, the probability of selecting the true model should typically go up. And that is where researchers have said MSE, mean squared error, is inconsistent because it does not penalize the degrees of freedom. There is no way we are changing the value based on the degrees of freedom or the sample size. But if you look at S squared, yes, error divided by T minus K. Error squared divided by T minus K. So there is a penalty for degrees of freedom. But that kind of penalization is not enough to render it as a consistent model. Whereas when it comes to AIC and SIC, both of them, they have a penalty on degrees of freedom. One of them is penalizing as e to the power of 2k by t. The other one is penalizing based on t to the power of k by t. So they are penalizing based on the degrees of freedom. more heavily than S squared, but even in case of AIC, we are seeing it inconsistent itself. As the sample size is getting larger and larger, we don't see the penalty to be quite heavily applied. Whereas the penalty is much heavily applied in case of SIC, because we are talking about t raised to power of k by t. So the penalty is much heavier in case of SIT. So what we see is SIC is much more a consistent model compared to AIC. So when we are making our results, when we are making our conclusions, making a conclusion based on SIC is much more appropriate compared to using S squared or MSE or AIC for that purpose. And we know that the true DGP and the best approximation. So we know, see, none of the models could be the could be exact representation of the true data generation process. So when I'm looking at the best approximation, first of all, these two may not be anywhere closer to each other. So they are very complicated than any model which we are fitting. So what we really need to see is we need to try many more sets of models as the sample size grows. But whatever is the result, out of all the various selection parameters that we are using, selection criteria that we are using SIC as a selection criteria would be much more appropriate. Using SIC as a selection criteria would be much more consistent for evaluating between the models compared to using any other model selection criteria per se. Alright. So this is what I really wanted to look at as a part of this session. We have covered the Excel way of looking at each of the forecasting trend forecasting models. We have estimated the trend, we have forecasted it for the next period, we looked at what is the 95% interval that is associated with the prediction, how much is the error that is present in the forecast, and along with that we also looked at what are the various kinds of criteria that I can use to compare between the models. So I hope you have got a decent amount of understanding in terms of usage of various trend-based models. Any further queries on the same, you can very well get in touch with me by giving me a call on the number that I have given below, or you can send in an email at the email address that I have provided below. Thanks a lot for listening to this session. Thank you very much.